One question you might have now is, can you do that process with any f of x function you want? Can you always find a series for it? And the answer is no. For example, let's do one that's immediately a problem. What if I was going to do 1 over x? Think for a minute to yourself, why might this be a problem? Think about what the graph looks like. Go ahead, think about it. So the graph of this is not defined at x equals 0. And as you noticed, the whole process that we had involved setting f of 0 equal to p of 0 and f prime of 0 equal to p prime of 0 and so on. So in this case, f of 0 is undefined because there is no y value at that x value. So right away, we can't construct a series representation for this. At least not one that I've shown you so far. What about a different one? Let's imagine f of x equals cube root of x. So this one doesn't have a problem. Cube root of x looks something like this. And it has a y value at 0, so I can definitely set the two y values equal. But the problem here comes when I need to set the first derivatives equal. The first derivative of this function gives me a vertical tangent line at x equals 0. So the first derivative is going to be undefined. So this is another function for which we won't be able to find an infinite polynomial. So in general, the requirement is, if I want to be able to perform this process, I need all of these derivatives to exist. In other words, your function has to be infinitely differentiable at the point x equals 0 in order to construct an infinitely accurate representation. Ta-da! Now you might be wondering, maybe there's some way of getting around this limitation. The whole problem with these is that we're trying to construct our approximation starting with a tangent line at x equals 0 and then improving that tangent line by making it higher and higher degree. Well, why 0? Why should we start at 0? Can't we build our approximation somewhere else so that we won't have a problem with our values being undefined? That's what we'll look at next time.